All right, this video is about vector operations, and really this is day one of vectors, okay? So here's your friend Vector from Despicable Me. He's going to help us through this, all right? So first of all, what is a vector? Well, a vector is a quantity that has both magnitude, which means a speed or a force, and a direction. And if you've been in physics, you know this. You've been through this. So it has what's called an initial point, a terminal point, a horizontal component, think of that as x, and a vertical component, think of that as y. Okay, so I'm going to call that an I for initial, a T for terminal. And then with notation, it has two V's, and I think V for vector. So it always goes horizontal and vertical, just like an XY coordinate would, but you know it's a vector if it has the sideways V's. All right, so here's our horizontal, here's our vertical, here's the initial part of the vector, and here's the terminal end of the vector. All right. So vectors can happen out anywhere in space. They always have a magnitude and a direction. Now, there's something called a component form of a vector. All right. So if the initial point is this, x1, y1, and the terminal point is x2, y2, then the component form of the vector is simply this: the second x minus the first x, the second y minus the first y, yielding the vector, notice the V's now, v1, v2. All right, so why do we mess with this? Well, because we are accustomed to graphs starting at the origin and moving out, but sometimes vectors are all the way out here, and how do they actually look? Like, what does that combination look like? Well, we can convert it to what's called a component form that could be written from the origin. That's where we're going with this whole idea. All right, so let's try this. It's really just simple subtraction. Okay, if the initial point is -3, 5, and the terminal point, we'll think that terminal point is 2, -4, write the component form of the vector. So initial to terminal, it's always going to be terminal minus initial on your x's, and then on your y's, it's terminal minus initial. So what's my terminal x? It's 2 minus my initial x, which is -3, so I add 3. Terminal y is -4 minus terminal or initial y, which was 5. So the component form of my vector then is 5, -9. And that's all there is to finding component form. It's pretty simple. Calculating magnitude. All right, calculating magnitude is important because it helps us know the strength of the vector. How much force does it have? How much speed does it have? How strong is this vector in movement? All right. So remember, our initial point is down here, x1, y1, and our terminal point is up here. All right. And we've done all the work, and now we know we've found our x1 or our v1, v2, which is really just our component form of the vector. We found this part of it. All right. So what is that telling you? V1 is your horizontal distance. V2 is your vertical distance, right? Well, isn't this making a right triangle? Isn't that what it is? So guess what? Your hypotenuse is what we call the magnitude. All right, that's the magnitude. So we could write it like this: V1 squared plus V2 squared equals the magnitude squared. All right, so to solve for magnitude, I really want to take the square root of all of this. So I have V1 squared plus V2 squared. If I take the square root of that sum, then I will have the magnitude. All right, and we notate magnitude with 2 lines on either side of our vector. Okay, so let's walk through this example. If the initial point is 2, 7, the terminal point is 1, -3, write the component form, that's one problem, and then of the vector, that's one problem, and the magnitude, that's the second problem. So we'll do component first. Okay, remember, component is terminal x minus initial x, terminal y minus the initial y. So let's clean that up. That's -1, and this is -10. So there's my component form of the vector. Magnitude, we just said the magnitude of this vector, and I call it v, little arrow, is going to be the square root of the v1, which was -1, squared, plus the v2, which is -10 squared? Well, 1 squared is 1. 10 squared is 100. So basically, I'm looking at the square root of 101. And you'll use your calculators. And we're going to round to 2 decimals. And I'll get 10.05. That is the magnitude of that vector. Okay? So look, component form from earlier examples, and then magnitude, we just use Pythagorean theorem to find it. Next, something called standard angles versus directional angles. Now, standard angles are what you're comfortable with. That's what we've always done so far in pre-cal. Everything is started here and went this direction, right? No news there. That's called a standard angle. Now, a directional angle, and you'll hear that a lot in this unit, or a bearing, are navigational angles that are measured from due north. If they're given with the north, south, east, and west notation, then it's measured from the north-south line. Okay, so what does that even mean? That means if you think about your normal grid, up here in standard angles, we know this is 0, 90, 180, 270, right? Well, if it's a directional angle, it's different. Everything is measured from the vertical. So this is really 0 degrees here. Now, what does that even mean? Well, let's say you're going to get a lot of angles in this unit, and it's going to be in the form of a direction. So something like north 25 degrees west. Well, hopefully you know your north, east, south, and west. Northwest is up here in this quadrant, right? But that 25 degrees is this angle right here. This is 25 degrees, all right? So your job is to be able to convert that back to a standard angle. So I know that if this is 25 degrees past my 90 degree, right, the standard form of this angle is going to be 90 plus 25, which is 115 degrees, right? So this is standard versus directional angle. And you'll be asked to do that quite a bit. So make sure you don't forget where you started with your standard angles. All right, on example 3, draw an angle 43 degrees southeast and convert it to a standard angle. Okay, so south and east means it's down here. Hopefully you know that. But remember, the 43 goes with the vertical, so it sits over here. That's a 43. So then my job is to figure out what is the standard angle that starts here and ends right there. All right, so think about what you know about the quadrants. This is 270 degrees, right? And I'm adding 43. So 270 plus 43 gives me 313 degrees. That's the standard angle for this directional angle. Let's try another one. Draw the angle northeast 17 degrees and convert it to a standard angle. Well, northeast 17 degrees is right there. It doesn't go with the, or if it has the direction on it, it goes beside the y-axis. Okay, I'm going to say that again. If it has direction on it, it goes beside the y-axis. And then to make it standard, you need to find the angle that starts at 0 and goes this way until it meets up. All right, so think about this. In this quadrant, that's all of 90 degrees, right? So 90 minus 17 gives me 73 degrees. And that's my standard angle for that directional angle. So on this one, I want you to try it on your own. All I'm asking you to do on this is find the component form and the magnitude. All right, good luck, and we'll see you in class.